this. So the title of chapter 12 is these vector valued functions. And so, this really kind of seems new at first. Here's one. R of t equals okay, I'm gonna make up an abstract thing, but what I have is, it's a vector value function. So what I have is an x component that might be a function of t. See, if I wanted to talk abstractly, I would say I have an x component that's a function of t, I have a y component that's a function of t, and then I have a z component that's a function of t. So I am talking abstractly. But what I could do is, this could be a t squared, a t cubed, e to the t, functions of t. And then here I am in 3 dimensions. We call this a space curve. And so it is not a surface. We're still kind of in the middle of studying surfaces. Right there at the end of chapter 11, we learned about a lot more surfaces, about cylindrical surfaces and quadric surfaces. And earlier in chapter 11, we did planes and spheres or surfaces. These are not surfaces. A curve in space. A curve in space. Of course, I drew it on the board. It looks like it's in 2 dimensions, but I'm saying it could be in space. It's in 3 dimensions. A curve in space. You put little arrows on the curve to kind of show the direction of motion, or what's called the direction of increasing t. So there sort of is a direction. If it's here at t equals 1, and then it's here at t equals 2, then I've got the correct arrows and the correct direction of motion going on here. That's called showing orientation. Show orientation. Or let me just define that as direction of increasing t. So again, I just wrote an abstract picture on the board here. Direction of increasing t. Showing orientation. And it's just a curve, an infinitesimally thin line. But it can curve. So not a line. If I'm in 2D, and I can do a lot of this in 2D, so I'm in 2D and 3D, kind of the rest of this course. I'm either in 2D or 3D. And really, we're always in 3D. But you can pretend for some problems, z equals 0, and you're in the xy plane. You can do 2-dimensional stuff. So if it is a 2-dimensional curve, then it's just in the xy plane. It's x of t, comma, y of t, I guess. And then the terminology is plane curve instead of space curve. It's a plane curve because it's in 2 dimensions. Of course, it's much easier to draw and think and analyze in these 2 dimensions. It's a little trickier with the 3-dimensional stuff. So let's do a good example of a plane curve. Here, this is a classic example. R of t is this. T, comma, t squared. So it's a 2-dimensional vector valued function. It's called a vector value function, I guess, because what you do is you input scalar values, t, you input t values, but the output is a vector. So the value of the function is a vector, r of t. So if I input a -2, you plug it into the vector valued function and you get a vector as output. You plug in a number, you input a scalar number for t, the output is a vector valued function in component form. It is -2, 4. Right, you guys? If you plug in a -1, you get the vector. You can do it.
negative 1, 1.
Thank you very much. Plug in the scalar 0, you get the vector 0, 0. Plug in a 1, you get the vector 1, 1. Plug in a 2, you get the vector 2, 4. I mean, I could go on forever here. What I'd like to do now is show you how you plot this. You plot this in the xy plane. And, you know, this is a hell of a lot like, I mean, almost exactly like, well, parametric equations where you plug in t's and you get x and y values. But what's funny is it's structured in the form of this vector. So what I've just plotted, what I'm about to plot here are these position vectors. These are position vectors. And so let's just check this out. So when t is negative 2, you get this position vector, negative 2, 4. Well, how do you draw a vector negative 2, 4? You draw him from the origin over 2 and up 4. And here's a picture of that vector. Of course, this is this concept again. The vector negative 2, 4 takes me to the point negative 2, 4. And, you know, I never wanted to say that points are the same as vectors, and I still don't want to say points are the same as vectors. Points are points, vectors are vectors, but it is true. The vector negative 2, 4 takes you to the point negative 2, 4. And in this chapter, let's about negative 1, 1. Negative 1, 1. That's this little vector, took me to that point. What about 0, 0? That's a funny vector. It goes nowhere, right? 0, 0, it goes right here. It's that point. 1, 1 is a vector. It starts at the origin, goes over 1 and up 1. That's the vector 1, 1. 2, 4 goes over 2 and up 4. Over 2, up 4. So I'm plotting these position vectors. The truth is, what I really want to do is sort of connect the points where these position vectors end up. I mean, that's really what I want to do, you guys. I want to connect the points where these position vectors end up. These position vectors take me to these positions. These are positions on this curve. This plane curve is, of course, this famous parabola, actually. Maybe you knew that. It does have, you know, back in the day when we used to sketch parabolas, we would put little arrows on it and say, oh yeah, it goes up in both directions. Hold on. In this new world here, I don't want to put those arrows on it. I might want to put arrows. I might want to show the orientation of the curve with arrows. And what is the orientation of the curve? The orientation of this curve is left to right, I think. Remember, if you remember, this was negative 2, negative 1, 0, 1, and 2. So the direction of increasing t is this way. I'm putting little arrows on my, that's the direct, not only now is it a curve, but there's a direction to the curve, an orientation to the curve. And then my picture's messy, man. I don't like all those little position vectors that I drew. I mean, those position vectors are part of the process. They take me to the points that are on the curve. They take me to the points that are on the curve, but the truth is I don't want to see them. I don't want to see all them damn vectors, so I want to erase them. I mean, is that okay? There are position vectors that plot these points, or these vectors take you to points. You connect those points with a curve, and that's how you generate this curve. I mean, that's it. That's the beginning of vector valued functions. That you plot points. Technically, you're plotting position vectors, which take you to points. It's just that subtle thing. Vectors are points, kind of almost in this world, though. You can almost make that equate. Vectors are points in this language, in this way we talk. I mean, it's subtle. That's not really true. Oh, I shouldn't say that. Now listen, this should have been sort of familiar to you. I mean, actually, no, the vectors are new to you, but the plotting of functions in relation to t. See, I don't know. I'm not sure what you guys did exactly in Cal 2. At the end of Cal 2, Chapter 10, you should have had a pretty good discussion on parametric equations. And I would have, if I taught Cal 2, I would have walked in and first day of parametric equations, and I would have said, here's a set of parametric equations. X equals t, y equals t squared. Here, let's plot some points, you guys. And I would have plotted points like this. And I would have, when t is -2, you get -2, 4. And when t is -1, you get -1, 1. And I would have plotted these points. And I would have paid attention to the orientation, and I would have drawn this curve, and I would have put little arrows on it, because with parametric equations you talk about orientation, and so we did this in Chapter 10, and now we're doing this in Chapter 12, and god dang it, it's the same thing, except for the subtle structure of over here, I really am plotting points. Over here, I'm sort of tricking myself. I'm plotting vectors that take me to points. But this is better. This is way better. You know, Tim, let me tell you why it's better. It's way better, dude. It's so much better. And it's the same, but it's better when I start talking derivatives. Let me just say something. Back here, if I was talking derivatives, the derivative would be dy dx. And back here in Chapter 10, when I would talk of derivative, I would have to say it's dy dt over dx dt. That's the derivative. And I could do that. It wasn't that terrible, but I could work on this derivative. And then that would be the slope of the tangent line at any given point, blah, blah, blah. You know what the derivative is, I hope. We are. By the way, we didn't get to do a lot of calculus in Chapter 11. We will now. We're about to do derivatives. Anyway, the derivative's a little messy over here. Anyway, I'm not doing that. I want to do this derivative. Watch this. I don't take too long. I'm making a couple big points here. In fact, as soon as I say let's do a derivative, you guys, all of a sudden I'm in 12.2. So I quickly got through 12.1. The truth is I'm not through 12.1. I can back up. A lot more to say, but I want to make these connections here with you. So follow this lecture here. We plotted position vectors. We plotted a vector value function. If we take this derivative, somebody has to teach you the rules of this derivative, and they do that in 12.2. You know, they do some limits in 12.2. They do the limit as delta t approaches 0. You know, they go back to the original definition of differentiation with the limit definition and everything. I'd rather just get to the point and take this guy's derivative. Of course, somebody has to tell you some new rule. This is a new guy. How do we do derivatives of vectors like this? Well, we do the derivative of each component. Maybe that's what you would have guessed. And so I do the derivative of the t. With respect to t, the derivative of t is 1. Remember how to do derivatives? And then I do the derivative of t squared.
2t.
2t. And what I have is now a derivative vector value function, which is the derivative of him. And if you drew this vector value function, you draw him on the curve, actually, and he turns out to be a nice tangent vector to the curve. He's tangent to the curve. Let's do a second derivative, r double prime. R double prime of t. Can you do this derivative, please?
0, 2.
Thank you. What did you say?
0, 2.
2. Right. Right. Okay. So what did I just do? I think I went to 12.2 and taught you how to do derivatives. How do you do derivatives of vector valued functions? Oh, just do the derivative of each component separately. That's it. Do the derivative of him, do the derivative of him. You can do second derivatives. Okay, all right. Okay, you ready? Now I'm going to 12.3. All right. If this is a little particle traveling through space, if it's a space curve, or in the plane, if it's a plane curve, if this is a little particle traveling on this path, and this is the position of the particle, if it's the position of the particle, the distance as a function of time, then what is his derivative?
Velocity.
Velocity. So this derivative can be thought of as velocity in certain problems. And then what's the second derivative?
Acceleration.
Acceleration. And so this is what the book does to you. They kind of ease you into this, and I'm already in 12.3 now. In 12.1, they ease you into the concept of vector-valued functions. In 12.2, they say, oh, guess what, kids? You can do derivatives. And then they wait until 12.3 before they bring up these words. Oh, remember derivatives, kids. Derivatives are, if it's position, the first derivative is velocity, and the second derivative is acceleration. Yeah, I'm sort of talking 12.1 through 12.3 here. I mean, or I just did in a quick 15 minutes. But it's good because that's the damn point. Now here's what I'd like to do. I'd like to sketch these velocity and acceleration vectors on this position curve at the point, let's do this point. Let's say I'm at the point 2, 4. I'm here at t equals 2. So at t equals 2, where's my position? Well, I could use my position function and find out that I'm at 2, 4. Oh, I already knew that from the chart. At t equals 2, the position is this point 2, 4. And the vector that took me there is the vector from the origin over 2 and up 4, right? There was a position vector that went over 2 and up 4 and took me out there. You guys right? Remember that?
Yeah.
There was a position vector that took me to that point. There he is. I erased it just because it clutters up my picture, kind of. Okay, but anyway, I'm at that point. Now, let's find the velocity at that point. The velocity at this point t equals 2. Well, I've got a velocity formula right there. If you plug in 2, what is it? 1, 4. Yeah. Now look what I called it. I changed the name. It was r prime. What did I call it? V for velocity. I mean, I don't know. I can talk either way, right? I could call it r prime of 2. We are using this little vector symbol on these guys because these are vector-valued functions. Anyway, check out what you do with this thing. Where's good? I got a nice blue one. What you do with this one to draw it is you draw it on the curve. So you don't draw it from the origin. You go to the point where you're at. If you remember, we're at the point 2, 4. And then at the point 2, 4, draw the velocity vector 1, 4, which would be over 1 and up 4. And I guarantee you, every time you do it, if you do it correctly, it'll look like it's tangent to the curve. It's supposed to be tangent to the curve. That's my velocity vector. I'm a little particle traveling on this path, and at that moment, that's a picture of my velocity. And it's tangent to the curve. You know, if some reason the tracks broke, or the magnetic field broke, or something, whatever was keeping it on this path broke, it would head off in that direction. That's at this moment. It wants to go that way. Something's keeping it on the tracks, though. Something's keeping it on this path. So this velocity vector is always tangent to the curve. So it's always sort of changing direction, changing length. I mean, right now it's that long. It's going that fast. Later it might be longer or shorter, longer. It's slowing down and speeding up. I guess it's got acceleration. What's the acceleration vector at this moment? At t equals 2, the acceleration vector at t equals 2, which could be called r double prime. Or what's another name for it? I called it r double prime, or I called it a. Can you think of another name?
Capital R triple prime?
No, that's a decent idea, but no. I meant it's r prime or r double prime. Well, wait. V prime, thank you. It could be V prime, right? it's V prime or it's r double prime, right? That's A, acceleration. And by the way, at 2, you plug 2 in there, what do you get?
0, 2.
You just get 0, 2. And we can draw that at this point. We can draw the acceleration vector. Acceleration is always red. Well, not always, but. And what do? 0, 2. Here he is. There's a little picture of the acceleration vector at this moment. These are the kinds of questions I like you to do. I like you to, but they're tougher than this. I started with a nice, easy, basic parabola, but we like to do this with circles and ellipses and other weird shapes. We like to sketch the curve and draw the velocity and acceleration vectors at a certain point. Calculate them and draw them. I mean, this is again, I get to the point usually of what I want you to know and think you should know. And this is it. This is it. Yeah, that's awesome, you guys. You know, look at that. That acceleration vector is kind of in the. And by the way, he's supposed to be straight up. 0, 2, straight up. But he's kind of in the direction of velocity. I mean, he's not in the direction. He's not exactly in the direction, but he's kind of in the direction of velocity. I mean, here's the question I want to ask you. Based on this picture, now that you see this, at this moment in time, is this particle speeding up, slowing down, or neither?
It's accelerating. Speeding up.
Is it speeding up, slowing down, or neither? You say speeding up? What do you say?
Neither.
Well, why do you say it's speeding up?
Because acceleration and velocity are in very roughly, the same direction.
That's a good explanation. That's how I thought. Now, and as we progress through this chapter, I'll have a more sophisticated way of talking on why it's speeding up. But you're right. Look, the acceleration and velocity are generally in the same direction. So the acceleration is helping the velocity. In the next picture frame, in the next instant, I bet that velocity vector is a little bit longer. I bet it grew. It sped up. The acceleration helped it.